So, good afternoon, everyone, and I'd like to start off by thanking my many co-authors who all contributed to this work, either through measurements or help with the analysis. I'd like to acknowledge funding from the NASA SEACRS and ACDAM programs, and I'd also like to thank all of the other speakers in this session for setting me up really nicely for this talk. So, as we've heard in great detail today, the forest is a really exciting place to do atmospheric chemistry because there are a lot of dynamic processes that control atmospheric composition in this environment. And as we know, there are a lot of uncertainties in each of these processes. So if you're thinking about where you would want to go in the United States to study this, you could look, for example, at a map of the Megan isoprene emission factors, and you should see this giant green blob here in the center of the country. This is the Ozark Mountains, which is also referred to as the Isoprene volcano. And I just want to set the record straight. Christine Wiedenmeyer is the one who should get credit for that name. And during the NASA SEACRS campaign, we had the chance to fly the DC-8 in this region. And this is a flight that Paul Wenberg talked about this morning. So a little bit after noon on September 6th, we came in from the east here, and we did a set of 4 stacked level legs, all in the boundary layer, going roughly from east to west. The wind was coming out of the southeast here, which you can see is just completely covered in oak trees. And this plot shows a time series of a few key tracers from this flight segment. I've got up here the direction of the flight, and then the altitude for each of those legs. Isoprene is in green, formaldehyde in blue, and then NO in red. And you may be drawn to this section here on the eastern part of the leg, transect, which is really interesting, and as Paul alluded to, the reasons for this are related to elevated OH there. It's a talk for another day. What I want to focus on are the grade regions, which is the cleaner central and western portions of the transect, where we had NO around 50 parts per trillion and isoprene ranging from 4 to 8 parts per billion. Now, the reason we flew the plane the way we did is because we wanted to try something that, to my knowledge, has not been done before from the DC-8, and that is to calculate eddy covariance fluxes of a whole range of reactive gases. And just to give you an idea of how this works, this is a partial time series from one of these transects. The vertical wind speed shown in brown, and then the isoprene variations relative to its mean value are shown in green. And you see what you expect, which is that when the wind is going up, isoprene is elevated because it's emitted at the surface, and then when the wind is going down, the isoprene is depleted because it's been reacted away. In other words, the flux, which is just the time average product of these two traces, contains information on both the emissions and the chemistry. And we're going to use that idea to our advantage here. The table on the right shows some of the species for which I've done these calculations, and the DC-8 is a giant bus. It has lots of great measurements, and I really have to thank all of the different groups that contributed to this work. And I want to stress that having this really complete set of measurements is critical for developing a self-consistent picture of the boundary layer. Okay, so what we're going to do is calculate one flux for each of those 4 segments, so you're going to see a lot of vertical profiles like this. This is, for example, the isoprene flux. Altitude here is normalized by the boundary layer height of 1 kilometer. The bars represent 95% confidence intervals, and then the line is just a fit through that. The way we analyze these kinds of measurements is just using the mass balance or the continuity equation, which sends the time rate of change of some species in a box is equal to in situ production and loss, which I lump into Q, minus the horizontal advection in and out, minus the rate of vertical advection or vertical flux in and out. If you rearrange this equation and integrate over height, you can find this and make some additional assumptions, you find this very nice linear relationship for flux as a function of altitude, where the slope is determined by these terms here, and I'll just mention that we can calculate advection and storage from the data that we have. And then the intercept tells you something about emission or deposition. So because of that relationship, which is not always that simple, it's not always linear, but the idea is that you can use these fluxes to get direct constraints on the rates of the physical and chemical processes. So this laundry list summarizes all of the parameters and processes for which I've been able to get some quantitative values, and I don't have time to talk about them all in 12 minutes. So I just want to focus on the ones that are shown here in black. And the theme here is the life cycle of isoprene. Okay, so we're going to talk about isoprene emissions, the oxidants that consume it, the products that it makes, and then what happens to those products. Okay, so let's start talking about isoprene emissions. So in theory, if we extrapolate this flux profile to the surface, we get an estimate for the emission, and then we can, for example, compare it with the latest version of Megan as determined by GeoSchem. And we find, similar to other studies that have been done and a few other talks earlier today, that Megan is overestimating isoprene emissions in the Ozarks, even with the latest updates. And I think it's worth pointing out here that airborne fluxes can quantify emissions over very diverse surfaces and conditions, so you can fly over a whole range of areas and really try to map out the variability and pinpoint where the problems are in the parameterization and try to improve it. And Paul Mishtal had a very nice paper on this year, and I understand he's going to have another one out very soon dealing with measurements from the Cabernet mission. Okay, so in these high isoprene environments, we know that we have problems with HOX. So models often predict less OH than what the measurements observe, and there's been a lot of debate over how much of that is because of the mechanism and how much of that is because of artifacts in the measurements. We can use these flux measurements to infer OH and HO2 concentration simply using the fact that the slope of this isoprene flux profile is proportional to its loss rate, mainly due to reaction with OH. Similarly, the positive slope of the hydrogen peroxide flux is due to its production rate through cross reactions of HO2. So you just invert those equations, you get values for OH and HO2 averaged over the whole transect here, and we can, for example, compare that with a model calculation such as a highly constrained master chemical mechanism or from GeoSchem. And for HO2, we find fairly good agreement here. But for OH, the zero-dimensional box model is underpredicting by about 30%. GeoSchem is underpredicting by a much larger factor, and that is, again, consistent with an overprediction of isoprene in this region. So consistent with a lot of these other studies, we find here that the models seem to have trouble getting OH in this high isoprene low NOx environment. And I hope you can see how valuable these kinds of measurements would be if they were done alongside measurements of OH and HO2, which, as we know, are very challenging. Okay, so I think we've seen versions of this figure many times today, so I won't dwell on it too much. You make these isoprene peroxy radicals. They can undergo a number of different fates to make hydroperoxyaldehydes, isoprene epoxides, and isoprene peroxides, or a minor channel is to react with NO and form isoprene nitrates. The yield over here on the right is specific to this particular environment, so it's just a fraction of isopo2 that makes that product. So what we can do is calculate the production and loss for each of these compounds using rate constants and so on from the literature and our measurements to determine and integrate that over height to get a chemical flux profile, which we can then compare with the observed flux profile, and if there's a difference, we know that we're missing a source or a sink. Okay, so I'm going to start with the isomerization chemistry here. So this chemistry was originally proposed in 2009 by the group at Leuven, and it has the potential to fix a lot of these discrepancies that we have in modeled and measured OH because it makes a lot of HOX when you put it in a model. However, the linchpin of this chemistry is the rate of the isomerization itself. So the current best theoretical estimate is still a factor of 1.8 times faster than what has been observed in chamber studies. So we'd like to be able to get another constraint on that. This plot shows the hydroperoxyaldehyde flux profile, and then the black line here is our calculation using the slower isomerization rate. And then you can see I just have to adjust for a deposition term here, and I get fairly good agreement with the observed flux profile. So we would say that the observations here are consistent with the relatively slow experimental isomerization rate, and to my knowledge, this is the first observational field confirmation of that slow isomerization. Okay, another hot topic that Jose talked quite a bit about today was formation of secondary organic aerosol from isoprene epoxides. Now, the Caltech instrument gives us the sum of these two, so these green bars show the measured flux profile for both of those. And then this is the calculated profile, basically using only gas phase chemistry and law, so I haven't included any aerosol chemistry here. And you can't tell, but there is actually a tiny difference in the slopes here. And so you can use that to estimate a missing rate. And then along with an estimate of aerosol surface area, I can back out a value for the reactive uptake coefficient gamma, which is just the probability that when the molecule strikes an aerosol, it will be lost to that aerosol. And this is the value that you would need to put into a model, for example. And the number that I get, based on, not surprisingly, given the slopes are the same here, is basically 0, okay, within my uncertainty. And you can compare that with a recent literature estimate and calculation, and you would get a much higher value of about 0.037. So there's a couple of potential explanations here. It could be that the uptake is suppressed by an organic coating, although I don't think that is sufficient to explain the size of that discrepancy. It's also possible that I haven't calculated aerosol pH properly. So this parameterization depends very, very sensitively on aerosol pH, and we know that that is very difficult to determine accurately. And I've used aerosol mass spectrometer measurements, thank you, Jose, to do the best I can to get that. But if that is incorrect, then my calculation from the Gaston parameterization is wrong. Regardless, this is something that we need to look into further. Okay. Isoprene nitrates, we get a different story here. So again, this is the measured profile. Now here's the calculation using gas phase production and loss, and there's a big difference in the slopes. That difference in the slopes tells us that we have to be missing a sink. And assuming that I got all the gas phase chemistry correct, the aerosol chemistry is the next easiest process to pick on. So again, using the difference in those slopes, estimate of aerosol surface area, I can back out a value of gamma of 0.021. Now, Paul Wenberg in his talk this morning estimated about 0.04. Okay, so there's a little difference there. But this is really fast. If this is true, this is the dominant sink for isoprene nitrates. Okay, its lifetime is 1/4 of what it is for the gas phase losses. And it's potentially a significant source of SOA mass from isoprene in this environment. Unfortunately, there are no, that I know of, lab parameterizations that I can compare to. So I'm hoping somebody in this audience will be motivated to go back to their lab and do the measurements that we need so that we can do a comparison here and figure out whether or not this is important. And this is also consistent with some of the other talks this morning. Okay, so now this is the same cartoon I showed you before. I just filled it in with all of the parameters that I was able to derive from this analysis. And keep in mind, as I said, this is only about half of the work that I've done here. I didn't even talk about deposition and other things. And this is only 1 hour of one flight from one campaign. So imagine what you could do with an entire campaign's worth of this type of data. This laundry list just shows you some of the sillier ideas that I've had about things that we could do with this. And I encourage you to pick your favorite idea off this list and talk about it over lunch, because I think we really only scratched the surface with what is possible here. So with that, I'll thank you and take questions. Yes, Paul.
The difference, I think, between 0.02 and 0.04 was we were thinking that only the 1,2 would hydrolyze.
Right, and I just have the sum
And you
here.
have the sum, so
Yeah.
you have something quite a bit lower.
Right. Yes.
So for your calculated gamma values for isoprene nitrates, is that just for first-generation isoprene nitrates? And if so, have you looked at whether there's a change when you look at second-generation species as well?
Yeah, so of course the Caltech instrument can measure everything. And that's only the first generation total isoprene nitrates. I do have measurements of the second generation ones, but the signal is so low in this environment that I cannot retrieve a reliable flux. So, you know, if that isoprene nitrate flux was very, very small, but it's still believable, but I haven't had any luck with the later generation ones.
Is it possible to derive particle fluxes from this data set?
Yeah, well, yes, in theory. And I tried with the AMS data, and they weren't sampling very quickly. And, you know, particle fluxes, as some other papers have shown, are very difficult. But I think in the future, it's something we want to try. Yeah.
All right, well, thanks again, and I hope to see you in the afternoon for the third session.